Okay, perfect. Thank you so much. Thank you so much for giving me this opportunity to share my research with everyone. So hello, good afternoon, good evening to everyone from everywhere in the world. I'm Aniruddh Vashisth. I'm currently an affiliate assistant professor, and as Jing mentioned, I'll be starting as a full-time assistant professor at University of Washington beginning of next year. I'll show you a little bit of my work that I've done on reactive molecular dynamics and experimental mechanics to understand polymer behavior and some derivatives of polymers as well. So as Jing also mentioned it really nicely, my journey kind of has been like from IIT-BHU to Penn State, to Texas A&M, and now the next stage is going to be University of Washington. And I have thoroughly enjoyed each and every step of my research progression, so as to say. So I'll start off with this very interesting graph by Michael Ashby, this Ashby plots. And if you look at the four different materials that he talks about: ceramics, composites, polymers, and metals, you can see that in the last 5 to 6 decades, the relative importance of these three materials, polymer, composites, and ceramics, has gone up tremendously. And if I just look at the last 3 decades in my lifespan, this importance has gone up relatively fast. And this is primarily due to applications of polymer, composites, and ceramics in automobile industry, aerospace industry, where lightweighting has become kind of an essential part. And if you just look at this very interesting age that he calls the age of molecular engineering. So Michael Ashby says that now we are in the age of molecular engineering, where if you can tweak the molecular structure of your material, you can kind of tailor or enhance the properties according to the end product that you require. So that's really interesting. So my work is mostly concentrated on these three materials. So I'm kind of fortunate that I kind of landed working in these three materials. So I'll tell you a little bit more about my research. The centroid of my research is mechanics of materials. So I've done a bunch of work on fiber composites. So my PhD at Penn State was mainly focused on toughened fiber composites, ballistic impact on composites. So this work was done in collaboration with NASA and Army Research Lab. I worked on bio-inspired composites during my MS at Penn State. So these are shape and stiffness changing composites. During my postdoc, I worked on polymer-derived ceramics. So I'll talk a little bit about these materials in today's talk as well. So we looked at the mechanical properties as a function of size. So we basically studied the size effect of ceramic nanofibers. Another very interesting work that I was able to be a part of was rapid manufacturing using radio frequency waves. So here you can targetedly heat just the adhesive. So let's say, for example, you want to bond two substrates with the adhesive. You can target all the energy to the adhesive. It's pretty much like, if you think about it, like you basically have Superman as your friend, and he can use his laser eyes to just weld. But this is pretty interesting. And apart from that, I've done a bunch of work on reactive molecular dynamics. And this work has usually been in conjunction with some of the experiments. That kind of brings me to my next slide. Over the years, working with simulations and experiments has made me appreciate both of these methods a lot. So I strongly feel that to get a very holistic, complete picture of a problem, looking at a problem from both simulation and experimental point of view helps to understand and appreciate the problem a little bit more. And those of you who are wondering like what exactly dr is, like I was not sure what I should put with a double integral, so I just put like a delta of research. So I apologize any mathematicians who are on this call. So I worked on, so what I'll do is like, I'll just use this slide as my kind of my outline slide. So I'll talk about cross-linking of thermosetting polymers, laser-induced graphene from polymers, and polymer-derived ceramics. So I'll try to sum up what I've done on these three research projects that I've worked over the last few years, and try to show you how nicely like simulation and experimental methods marry each other, and you're able to get some very beautiful insights. So before I start that, I'll just give a brief introduction of atomistic simulations. So if you look at the time distance landscape, you can basically divide simulations into two subcategories. That you have super atomistic simulations. These are more or less like continuum based type of simulations, or simulations of work, and then there is atomistic simulations. Now, if we look closely at atomistic simulations, there's a further divide. We can further divide it into quantum mechanics. So these are ab initio, DFT, Hartree-Fock methods, pretty much the simulations that are based on first principle calculations. And these simulations are really nice. You can see bond formation, bond breaking, but the downside here is that you can only simulate a couple of hundred atoms. So that kind of restricts the size of the simulation that you can do. Another method is force field method. So these include empirical force fields. So here you can simulate really large systems. You can go up to a couple of thousand, maybe more than that in number of atoms. But you kind of lose the resolution that you get from quantum mechanics simulations. So what ReactFF, or reactor molecular dynamics, does is that it kind of bridges the gap between quantum mechanics and force field simulations. So using this method, you can simulate reactions in a large dynamic system. I was kind of fortunate that at Penn State, Professor Adrie Van Doyen, who was one of the co-inventors of this method, was my co-advisor. So I got to learn a lot from him and his group members, specifically Chaudhry Ashraf, who worked a lot with me. He was a PhD student with me. So getting back to the topic, ReactFF, or reactor molecular dynamics, it basically considers a ball and stick model where the atom is modeled as a ball and the bonds are modeled as a stick. So Dr. Van Doyen has a really nice, beautiful paper on kind of the evolution of ReactFF method. So, it started off in around 2001 as a simulation platform for hydrocarbons, and it has kind of grown into a bunch of different things. There has been a lot of studies on combustion, aqueous system, independent systems such as interaction of gases and nanoparticles. Going into my PhD project, one of my focus was using polymers, and not a lot had been done using ReactFF in terms of polymers. So the first project that I worked on was cross-linking of thermosetting polymers using ReactFF. So just to give you a little bit of motivation, like why we would want to do this, let's say somebody gives you thousands of epoxides or thousands of resin systems, and you need to figure out which one of these have the best thermomechanical properties, or a particular type of thermomechanical properties that you're looking for. It's going to be terribly difficult if you have to do experiment on so many polymers. So what molecular simulations can do is that you can reduce the number of physical experiments. You can run multiple simulations in parallel and figure out that, okay, X, Y, Z polymers give you the type of thermomechanical properties that you're actually looking for. So another challenge is that experimental cross-linking is very slow. So if you try to cure an epoxy, it takes a couple of hours. Sometimes it can take a couple of days as well. But in molecular dynamics, all you can do is you can simulate only a couple of nanoseconds. And usually what the way around that people have figured out is that what they'll do is they'll look at the curing agent, and they'll look at the epoxide. They'll say, once the reactive sites are within a certain distance from each other, they cross-link. They just react. They call it the cutoff method. Well, cutoff method is not exactly what's happening in your reactions. I mean, there are a bunch of different things that contribute to reaction. So what we did, we came up with this method that we call accelerated reactive method. So let's just consider the reactive sites, just the epoxide and the amine. So we agree that the first condition has to be similar to what people prior to us have done. We say that once these atoms, these molecules, reactive sites are within a certain distance from each other, that's criteria number one satisfied. Once this is done, what we do is that we provide these reactive sites with enough energy that it can go up to a transition state. And this energy that we provide the reactive sites, it's usually equal to the activation energy for that reaction. Then it's completely up to the reactants if they want to react or not. If the path of approach is really nice, they react. So for example, the video that you see here on the left bottom, you can see that the path of approach was really nice and the molecules were able to react with each other. There could be times where you would have some sort of a steric hindrance, you would have another molecule in between, and in this case, you would not see a reaction. And fortunately, this method has been implemented in a couple of softwares as well. Okay, so now that we have this algorithm with us, what we can do is, let's say we come back to that initial problem that I have a bucket of epoxides, you have a bucket of amines, and let's say you want to make a virtual polymer. So you can pick up one epoxide and one amine, or you can actually mix and match. You can pick up a couple of epoxides and one amine, and you can make a virtual polymer. And on this virtual polymer, you can do a bunch of experimental testing. You can do modulus, TG, coefficient of thermal expansion, density, atomic oxygen impact. So I'll show you one simulation of modulus here, where we examined the tensile testing. We did a virtual tensile test on this polymer. Usually, you have to complete your simulation within a couple of nanoseconds for molecular dynamics. So we have to do virtual experiments at really high strain rate. But we did some experiments as well at lower strain rates, and if we extrapolate our results, we see fairly good agreement. Some of the other experiments, virtual and physical experiments that we did, were TG, density, coefficient of thermal expansion, and we see a pretty spot on comparison between our experiments and the simulation. Now, there are some experiments that are terribly difficult to do in the lab. For example, atomic oxygen impact on polymers which are in lower Earth orbit. Like, this is going to be a really difficult experimental setup in your lab, because you need atomic oxygen to be traveling at a speed of 8 kilometers per second. So that's going to be terribly difficult, but through simulations, this is something that you can do and try to get some insights as to how a polymer behaves. Like, how does the polymer chemistry affect, or how does the polymer backbone gets affected by atomic oxygen impact. So for example, we did some simulations and found that if the backbone is aromatic in nature as compared to aliphatic or acyclic, the polymer is much more resistant to. So that's kind of the first project. Now I'll move on to the second project that I'll talk about. It's called laser-induced graphene. So it's a very interesting way of making. It's a single-step process of making a graphitic. As to say, you can say that it's not exactly graphene. It's not planar. It's kind of a foamy structure. So it kind of has some undulations in it. But the main process here is that you take a CO2 laser and you laze a polymer. And by lasing the polymer, you basically change the polymer into ordered graphitic structure. So it's a very interesting, very cheap, and a very straightforward way of making a highly conductive graphitic material. One of the things that I'm curious about is that can Jedis make a leg by putting their lightsabers into polymers? But I think that's a project for future. So some of the things that we tried. So we looked at, we did some scanning electron microscopy analysis on laser-induced graphene. So here's how laser-induced graphene looks like. You can see clearly it's kind of a foamy structure. And if you look at the Raman plots, you can see the G and D peaks, suggesting that there is some ordered graphitic structure there. And LIG has been used for various applications. So for example, microfluidics, composites, it has really good conductivity. So it's been used for sensors, for heating, for analysis, and a couple of other applications as well. So what our motivation was that, LIG could be made from so many different polymers. So we just wanted to understand how does the parent polymer affect gas evolution, like the type of yield you can get, what are the reaction pathways. There were so many interesting questions that could be answered using molecular dynamics. So what we did was that we looked at these 5 different types of polymers. All these 5 polymers have actually shown to make LIG when they are lased with a CO2 laser. So for example, here's a LIG structure that is made from Kapton. And as I mentioned earlier, it has a very interesting structure. You see there's a bunch of 6-member rings that are colored as light blue. There are 7-member rings that are colored as dark blue, and there are 5-member rings as well, which are colored as orange here. So it's a very interesting type of structure. It's not a planar structure because it has so many 5 and 7-member rings, but really interesting, like what exactly is happening as this molecule is getting formed. So here's a interesting comparison. Like you can see a virtually fabricated LIG, and you can see a high resolution TEM from one of James Tour's paper. Dr. Tour's lab actually invented this material at Rice University. So he has a really nice paper in Nature Communication where he has really high resolution TEM images. So we saw that in our simulations also. We see that 7-member rings, 6-member ring, 5-member rings that are also seen in high resolution TEM images for peak polymer that has been converted to LIG. We also looked at what are the different gases that are getting evolved. So for example, at 2800 Kelvin, if we look at CO2, carbon monoxide that is getting evolved, you see that Kapton lets CO2. And this is mainly because Kapton has a higher content of oxygen in it. And one of the reasons why you see such a foamy structure is because there's a lot of gas evolution as well. We also looked at H2 evolution, how much hydrogen is getting evolved. And basically the evolution of hydrogen is contributing to conversion of sp3 carbon to sp2 carbon. Coming back to parent polymer, we also looked at what is the yield for different polymers. So we looked at a bunch of different parameters. So for example, when you have to make LIG from a polymer, you look at a bunch of different parameters. You look at what is the input power that you want to use, how fast you want your laser to move. Similarly, in our simulations, we looked at what were the different ramp rates for the simulations, what is the pressure, environmental condition, target temperatures that we wanted to use. So if you look here, if you look here at different polymers, you can see that for PC, the yield actually increases at higher temperatures. But if you look at PBM, the yield kind of plateaus out at around 2800 degrees Celsius. So that's a very interesting observation if you look at that you require higher powers to get higher yield for polycarbonate as compared to PBM. Another very interesting observation that we saw was that the yield decreases when the simulations LIG conversion is carried out in oxygen, in the presence of oxygen. And that's kind of intuitive because a lot of your, the oxygen is kind of aiding in the oxidation of the polymer as well. But if you look carefully here, Kapton sees a much higher drop in yield as compared to peak or let's say PEI, which is also a very interesting observation. Next, we looked at the snapshots. So we looked at the simulation process very carefully, very minutely. And what happens is that when you start lasing a polymer, it converts into an amorphous structure. And this amorphous structure finally converts into a very ordered structure. If you look at how exactly the ring formations are happening during the whole process, you can see that there are these 6 different 6 carbon atoms, in the structure. They are kind of not all together during the amorphous phase, but once the order structure gets started to form, like you can see all these 6 carbon atoms getting together to make a 6-member ring. Actually, the 5-member ring is much more interesting. We saw this really interesting formation where these 6 carbon atoms actually make a 6-member ring. But if you look carefully, there's a 7-member ring and a 5-member ring adjacent to the 6-member ring, which causes a lot of steric forces in this 6-member ring. So I don't know how easily it is visible, but this carbon atom is trying to go out of plane. And what eventually happens is that that carbon atom breaks off and makes a 5-member ring eventually. So with that, like we looked at laser-induced graphene, like what were the different formation mechanisms, different polymers, how they behave to lasing parameters. We looked at different gases getting involved and like what are the yields for different. So this was also a very interesting study, which was kind of motivated by experiments, but most of the insight that we got, at least in this publication, by nanomaterials, was through simulations. Finally, I'll talk about polymer-derived ceramics. Again, this is also a very interesting, field, and this is something that I plan to pursue in the future as well, like examining polymer-derived ceramics. So what polymer-derived ceramics is like, I'll start with the chemistry of like how exactly you can make ceramics out of a polymer. So you have a molecule that has a silica-oxygen chain. And what happens is that you stabilize or you heat up this material in the presence of air in around temperatures close to 2700 to 300 degrees Celsius. And you kind of make, you have a lot of water molecules that come out, and you have a lot of SiO-Si type of bonds getting formed. Now, when you put this polymer, the stabilized compound, into a furnace, and you cook it at really high temperatures, temperatures close to 1000 degrees Celsius in inert atmosphere, what we call as pyrolysis, you have a bunch of hydrocarbons, siloxane, oligomers, and H2 that evolve. And finally, you have a structure that has carbon triple bond, carbon double bonds, and it has more silica carbon bonds, and it makes a very strong ceramic structure. And this is a very brittle, very strong ceramic structure. So what we did was that we made a precursor using this polymer. We dissolved this in a DMF solvent, and we used electrospinning, where basically you load up all this precursor in a syringe, and then you apply a potential between a syringe and a collector, and you basically make fibers using this process. We made fibers which had average diameter close to 1 micrometer. But as you can see here, the diameters actually varied from 200 nanometer to 2.2 micrometer. There was a wide variance of nanofibers that we got. What we wanted to do was that we wanted to look at the mechanical strength of these fibers, and this whole research project was kind of motivated by the fact that you have these gases that are evolving during this whole process, and how do these gases play into the final mechanical strength of your material. So for example, if you have this fiber that has been made and you're trying to cook this fiber, the gases would try to come out from center to outside on the surface of the fiber. But at the same time, if you look at this fiber, there's a competing mechanism that's going on. The fiber is actually solidifying on the periphery as well. So you have gases that are coming out, and you have fiber that is solidifying at the periphery. So there are two competing mechanisms, and we really wanted to know how exactly is it that these two mechanisms are competing with each other. So we did some strength test on fibers with different diameters. So we looked at diameters of around 110 nanometer to 600 nanometers. You might be wondering why we didn't go to much smaller diameters. That is because these fibers are so brittle that even if you try to touch them with your micro manipulators, they just fly away. So it's really difficult to pick these fibers once they become really small. Here's a schematic of a fractured broken fiber. And our thought process was that initially our thought process was that the strength of these fibers will go according to Griffith theory, which says that the strength is inversely proportional to the square root of the flaw. We assume that the biggest flaw that you can have is the size of the diameter of fiber. But that didn't quite happen. You know, we saw like a much rapid increase in the strength. So that kind of got us thinking like, what exactly could be happening? Kind of had a clue what was happening. So we carried out some molecular dynamic simulations of flawless materials. And we found that the strength, actually, the maximum strength that could be achieved by these fibers is around 8.5 GPa. Now, when we extrapolate our experimental results, this actually comes out at around 330 nanometer. So basically what we figured out was that once you get to fibers that are of diameter 330 nanometers, all the gases are able to escape the fiber before the solidification starts, which is a very interesting observation. So with this, like we were pretty confident, we went forward, we did some virtual testing at elevated temperatures as well. And I will note, like, that all these simulations were done in inert atmosphere. So they did not have any oxygen or water molecules present, which would be present in a real world scenario. And you can see we did some RDF, radial distribution function calculations, where you calculate what is the probability of seeing two carbon atoms close to each other at a particular distance. So this peak, which is correspondent to carbon-carbon single bond, sees a sharp decline as you increase the temperature, whereas two other peaks start to prop up at elevated, like start increasing your temperature. And this is because as you're increasing your temperature, you're also aiding formation of carbon double bonds and carbon triple bonds. So this was a very interesting observation from the simulation as well. With that, like I would like to conclude. So I showed you some of my work using reactive molecular dynamics on polymers and derivatives of polymers for understanding the relationship between polymers, polymer cross-linking, thermosetting polymers, reaction pathways for laser-induced graphene, and insight into mechanical properties of flawless polymer-derived ceramics. I would like to acknowledge professors at Penn State and Texas A&M, my colleagues and friends, my lab mates at Penn State, Texas A&M, and my friends, family, my wife's cat, who gives me these condescending views that always helps me to do better in life. And I'll be a little bit shameless here, and I'll publicize, like, if you want to join our lab at University of Washington, feel free to email us. Email me your CV at vashisth@uw.edu. Thank you so much, and I'm open to any questions.
Thank you. This is a wonderful talk. So maybe Sid, you ask your question, like during the talk, you can start to ask your question.
So, hey Aniruddh, thanks for the interesting talk. My name is Sid. I'm a postdoc at ETH. So I have a quick question from the computational perspective. So since you're dealing with long polymer chains or molecules, I can imagine that the simulation runtimes would be very long. So realistically, how large simulations are you able to simulate to obtain like statistically relevant properties? And have you looked into any temporal or spatial coarse graining methods?
So thank you. That's a really interesting question. So this method, like specifically, I think the of all the methods that I've shown you, I think the one that has been like the most computationally expensive one is accelerated reactive, where we try to simulate cross-linking of thermosetting polymers. Initially, like when I worked on it during my PhD, like we were just working on Python codes, and they really like they took a really long time. We were able to they basically took a couple of weeks to simulate a polymer with 10,000 atoms. But fortunately, this method actually got implemented. It was implemented in SEM, This is a company in the Netherlands. So they basically parallelize the code. And now actually I'm able to run those simulations on my desktop. Like I ran those simulations on my desktop, and it takes like a couple of days. So I feel like it's a 4-core desktop as compared to, like, I believe like I was using, like, I don't know, like can't even, like, I was using a lot of computational power. Like I know that Professor Van Doyen was like wild, like, what are you doing that you're using so much computational power? So like there has been like a lot of improvement in terms of computational power there. In terms of coarse graining these methods, like no, I haven't actually looked into that. That's kind of the area that I would want to explore in the future. But that's something that, like, that's kind of on the back burner right now. But like, something that will be probably within in the future. So yeah, thanks.
So what? Just one quick clarification. What did you say? SEM?
SEM, software for chemistry and materials. If you just Google SEM ADF, it'll come up.
Okay.
Yeah, so it's a industrially available like software. Yeah.
All right. Cool. Thank you.
Okay, we can allow for one more question. Ankush, you may ask your question.
Yeah, Professor Vashisth, my question is, can we predict exothermic reaction temperature during curing process in the polymers in Reacts RF?
I think you should be able to do that. It all depends. Like, like I didn't mention this during uh, during the talk, but these polymers, these simulations are carried out using something called as force fields. So force fields, you can think of it as like your material parameters. So you put material parameters in FEA simulation. Similarly, force fields are like material parameters that you put in for molecular dynamics. So if you have a really well-trained force field, I think you should be able to, I believe you should be able to do that.
Okay, and one quick question, like, can we oxidized LIG further, like for serialization or through Hammer's process?
I'm not really sure about that. I mean, I think through simulation, I'm pretty sure you can do that, but I'm not sure what the result would be like experimentally also, if it would be stable or not.
Okay,
I'm not completely sure about that.
okay. Thank you, Professor. Thank you.